Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's my pleasure to introduce Maria Paola Bonacina. She's a professor in the University of Verona. She's no stranger to us. She was a visiting researcher here in 2008. And this year she was a program chair of CADE, and she took in New York, and she took the opportunity to visit us this week here. Thank you.
Thank you very much. Okay, so thank you very much for coming. The talk is entitled Unfairness in Theorem-Proving. I'm going to go through some motivation and then distinguish two concepts: uniform fairness for saturation and fairness for theorem-proving. Now, what is the main message of this talk? The main message of this talk is that theorem-proving is search, not saturation. The relevant property to distinguish between search and saturation is fairness, which has to do with the control of the inferences rather than with the inferences themselves. And the message is that fairness really should earn us less than saturation, because saturation in a sense is too much for theorem proving. And fairness should consider not only expansion inference rules, namely the inference rules which deduce consequences from given premises, but also contraction inference rules, namely those inference rules which remove redundant formulae.
What do you mean by earn?
They yield, provide. Now, fairness is a common concept in computing. For instance, when it comes to scheduling, we are used to the idea that a schedule should be fair in the sense of preventing any process from starving. It is also a common concept in all applications which require a search, because in a search, we don't want to neglect moves that are useful. Now, the crucial point with defining fairness is exactly to determine what is useful. Now, fairness comes up a lot in automated reasoning, where we have essentially two ingredients. We have a system of rules, which we usually call inference system, but we can also call more generally transition system. And we have a search plan, which is responsible for guiding the search, for deciding which inferences to apply to which premises, and therefore guiding the search for a proof or a model. Now, the inference rules themselves are non-deterministic. They define the search space we have. The search plan is the ingredient which adds determinism, in the sense that once we have an input and the inference rules, we have many possible derivations. Once we also add a search plan, the derivation from a given input becomes unique, and therefore we do have a procedure at that point. So simply giving a set of inference rules doesn't really give us a procedure. We need to add a search plan to have a deterministic procedure. So a procedural strategy is always given by coupling these two ingredients, a system of rules and a search plan. Now, the typical requirements on these two is that for the system of rules, we want it to be complete, in the sense that there exist successful derivations. What does it mean to be successful? Well, if we are looking for a refutation, a successful derivation will be one which terminates with the empty clause, with the contradiction. If we are looking for a model, a successful derivation will be one that terminates with a model. Now, because the inference system determines many possible derivations, yes?
Just a clarification question about your
Yes.
last remark. So my understanding of inference systems were that you are inferring facts,
Yes.
meaning theorems, but you somehow overloaded the derivation to include both facts and models.
Well, because, in this talk, I'm going to talk about mostly theorem proving in the sense of semi-decision procedures for validity, for unsatisfiability, and therefore refutationally validity. But the concept of having a system of rules and a search plan, and therefore the issue of making sure that the search plan is fair, applies to any inference or transition system. It applies also to a decision procedure, which will give you a proof if the input is unsatisfiable and the model if the input is satisfiable. So these general concepts don't need to be given only for refutational theorem proving. They could be given also for model building. Now, the system of rules needs to make sure that there are derivations that are successful. The search plan needs to be fair, which means it needs to ensure that the unique derivation that the procedure will generate from the given input will be a successful one. Whenever successful derivations exist, we find one. Now, let's see, for instance, in theorem proving. In theorem proving, the completeness property we want to have is refutational completeness. If the input set is unsatisfiable, we want the inference system to generate derivations that arrive at the empty clause, and therefore at a proof. The search plan needs to be fair, means that the generated derivation should reach the contradiction. And therefore, a complete theorem proving strategy will be given by a refutationally complete inference system and the fair search plan in this sense. Now, the topic of this talk is fairness. Clearly, there is a brute force way to be fair, and that is to be exhaustive, consider eventually all applicable steps. But that's not especially promising. And nevertheless, it is amazing how much brute force exhaustive search still reasoning mechanisms and theorem provers do. The question is how to be fair without being exhaustive. So we want non-trivial definitions of fairness, non-trivial search plans. The idea is that non-trivial fairness will reduce the gap between completeness and efficiency, because we want somehow to reconcile these two, to preserve completeness and still have efficiency. Now, one could counter to this that in practice, we often work with systems that are not complete. So we give up on completeness. We have completeness in the papers, in the theorems, the meta-theorems about the systems. But then when we run the experiments with the theorem provers, we often give up on completeness for reasons of efficiency. That's true, but it's true that we give up on completeness in a controlled way by weakening a system of which we know upfront that it is complete. So we are still interested in fairness to know where to start from in order to weaken the system. And also we are interested in fairness because we would like to have non-trivial fair search plans that somehow reconcile completeness and efficiency. And this is a very long-term goal, and probably we are still far from that, but I think it is important to state it at least as a challenge. Now, remember what I said about search. We don't want to neglect anything that is useful, so the point is what is useful, what is needed in order to make sure that our derivation will be successful if in the realm of all possible derivations there exist successful ones. So what is useful, or even more stringent, what is needed? Now, dually, we can ask what is not needed, that is, what is redundant, what should not be done, because one way of focusing on what is needed is avoiding doing what is not needed. So this to state that two concepts that are very important in theorem proving, namely fairness and redundancy, are related. So let's take let's see a first notion of redundancy. Assume to have resolution and subsumption, two well-known inference rules. Then we can say that a clause is redundant if it can be subsumed. I assume we all know what is subsumption. A clause C can subsume a clause D if D is less general, which formally means that there exists a substitution sigma such that C sigma is a subset of D, where the clauses are seen as multisets. And then we can say that the subsumed clause is redundant. Let's see.
Can you go back one slide?
Yes.
So in that case, if C sigma is a subset of D, then which one is redundant, D or C?
D is redundant.
D is redundant.
Because C implies D. You know, whenever C is true, all its instances are true, therefore C sigma is true. And because C sigma is a subset and these are disjunctions, whenever C sigma is true, D is also true. So it can go away, the bigger clause. Another example, the notion of redundancy that we usually have when we couple superposition and simplification. Simplification is resolution with equality built in. We assume to have a well-founded ordering on terms and literals, and we superpose maximal sides of equations into maximal sides of other equations or maximal non-equational literals. Simplification uses this ordering to do well-founded rewriting. And then one definition of redundancy is the following that works well with these inference rules. We say that a ground clause D is redundant in a set S if there exist ground instances C1, Cn of clauses in S such that C1, Cn are smaller than D. We can see C1, Cn as a multiset and D as a multiset made of only one element and use the multiset extension of the ordering. And C1, Cn entail D. And then we can say that, now this is for a ground clause, and then we can say that the clause D is redundant if all its ground distances are. So this notion of redundancy is not related to a single inference rule like subsumption in the previous slide, but it says that the clause is redundant if there are smaller clauses that imply it, essentially.
So here,
yes.
Here I should read that funny less than as the conjunction of C1 to Cn implies D? Is that how I should read it?
Yes.
Okay.
C1, Cn, let's see. C1, Cn here is a set or a conjunction, and this one is logical entailment. So D is a logical consequence of C1, Cn.
And so what is the difference between, so there's a word and there. There's something to the left of and, there's something to the right of and. What is the difference between
Sorry, I don't see
this
what you mean.
and this?
Oh, okay. Sorry. This one says that C1, Cn are smaller in the ordering. So this ordering on terms and literals can be extended to clauses by using a multiset extension. And then it can be extended to multiset of clauses by doing another multiset extension. So we can compare the multiset of clauses containing C1, Cn with the multiset of clauses containing only D. And this guy essentially will be bigger than each of these. Okay. So we have smaller clauses that entail. Now, once we have a notion of redundancy for clauses, we can have also a notion of redundancy for inferences, because we can say that an inference is redundant if it uses or generates a redundant clause. Now, fairness is a global property, though. It does not apply to a single inference, it applies to the whole derivation. So we need to say when a derivation is redundant, is fair, and then a search plan is fair if all of the derivations it generates are. So we need to define the limit of a derivation because the derivation in theorem-proving is not necessarily finite. And the limit is defined as the set of persistent clauses. That is, clauses that appear at some point and never go away. That means to be persistent. Why do we need to define it in this way? Because we have both inference rules that generate clauses and inference rules that eliminate clauses. And so S infinity, the limit, will be defined as the union for all j greater or equal than 0 of the intersection for I greater or equal than j of the sets Si in the derivation. That means when j is equal to 0, we take the clauses that are in the input and that persist always. For j equal 1, we take those that appear at stage 1 and then always remain, and so on.
So this is, another way to say it is that this is the set of clauses that appear infinitely often. No, they only appear once, but then always remain. Always remain, yes.
Always remain. They never go away. Okay. Now, these are the definitions that are most common in the literature. So to say, and this is what is usually called fairness, but instead I call it uniform fairness, because the message of this talk is that this property of fairness is good for saturation, but it is somewhat too strong for theorem proving. So let's say that I sub E represent the clauses that can be generated from S by expansion. And then we have a derivation. So we say that the derivation is fair if for all clauses C that can be generated by expansion from persistent clauses, there exists a stage J where the clause either appears or is redundant.
I'm sorry, what does expansion mean?
Expansion is something like resolution, superposition, all those inference rules which add something. Okay. So they expand the set of existing clauses. Alternatively, in the literature, it has also been formulated in a slightly different way, which is equivalent. People say, for all clauses C that can be generated by expansion from non-redundant persistent premises, there exists a J such that C appears at stage J. Or equivalently, one can say all non-redundant expansion inferences are done eventually. And this is how fairness is usually defined. Now, the question is, can we have a weaker notion of fairness and claim that uniform fairness is for saturation and fairness is for theorem proving? Now, this can be done by working with the proof ordering rather than only with the formula ordering. The notion of proof ordering is also a classical notion in the theorem proving literature, and it appeared several years ago. There are papers by Leo Bachmeier, Nahum Dershowitz, and Leo Bachmeier, Nahum Dershowitz, and Jie Jiang on proof orderings. Now, one could say, well, what's the difference? Indeed, the proof ordering can agree with a formula ordering or reduce to a formula ordering if we compare proofs by their premises, which is what certainly can be done. But the notion of proof ordering is more flexible because we can actually have small proofs. We can define proof orderings in such a way that small proofs have large premises and vice versa. So it doesn't have to go exactly with the formula. Now, if we have a well-founded proof ordering, we can talk about proof reduction. So we call justification a set of proofs, and we can compare justifications. And we can say that a set of proofs Q is better than a set of proofs P if for all proofs in P, there exists a proof in Q which is smaller or equal. Now, the ordering is defined in such a way that we compare proofs of the same theorem, of course, so that it makes sense to compare them. If we have a proof ordering, not only we can compare sets of proofs, but we can also compare presentations by the proofs they make available. So say that S is a presentation of the theory THS. So THS is the set of all the theorems that follow from S. Then we denote by PF of S the set of proofs with premises in S. And then we can say that given two presentations S prime and S that are equivalent, so they are the presentation of the same theory, of the same deductively closed set of theorems, S prime is simpler than S, and therefore it's preferable intuitively, if the set of proofs of S prime is better than the set of proofs of S. So this was...
What is a presentation?
A presentation is a set of formulae or clauses which presents a theory. It's like an axiomatization. Presentation is a synonym for axiomatization. You have a bunch of formulae which present a theory in the sense that they define the set of all the theorems that are logical consequences of those formulae. But for a given set of theorems, you have more than one presentation, of course. So the presentations are equivalent, and one is simpler than the other if it has better proofs, according to the proof ordering. So smaller proofs according to the proof ordering. Now, again, with the well-founded proof ordering, we can look at the minimal proofs in a given set of proofs, P. So let's call mu of P the minimal proofs in the set of proofs P. And then we can define the normal form proofs, NF of S. How? We take S, we take its deductive closure, so TH of S is the deductively closed presentation. Then we take all the proofs in here, and then we take the minimal ones. And these are the normal form proofs. So for any set of proofs, because the ordering is well-founded, we can look at the minimal ones. Normal form proofs ones are the minimal ones if ideally I could consider as presentation the whole set of theorems. Now, of course, this is not something that I have in practice, because in practice I have a concrete presentation. I don't have, and I don't even want to have, the whole set of theorems. But I'm going to be interested in a normal form proof of the one theorem I want to prove. So the normal form proof is the minimal proof with respect to all possible formulae that follow from the presentation and that I could use to build that best proof. Now, here comes an important distinction. I said we would like to have a notion of fairness which gives us something weaker than saturation. So we need a weaker notion than saturated set. Now, we call saturated a set, a presentation, which provides all the normal form proofs. We call complete a presentation which provides at least one normal form proof for every theorem. Now, the two will coincide if minimal proofs are unique, for instance, if the proof ordering is total. However, this is not necessarily the case, because in general, orderings and proof orderings are partial. So in many cases, we can distinguish these two. In the complete, we only have one normal form proof. In the saturated, we have them all. Let's see an example. Assume we have only three equations, A equal B, B equals C, and A equals C. And assume that we consider as minimal proofs the valley proofs, which means the proof that prove that S is equal to T by rewriting S and T to a common form. So what we have here, this is rewriting 0 or more steps, because there is a star over the arrow for rewriting. This is just composition. So this means there exists some term U such that S rewrites to U and T rewrites to U, and this happens by pure rewriting. So basically we have something like this. Which goes down to a common form. Now, if A is greater than B and B is greater than C is the ordering, B equals C and A equals C is a complete presentation for the above set. We do not need the equation A equal B, because the valley proof A goes to C by A equals C, since A is greater than C, and B goes to C by B equals C, since B is greater than C, gives me a minimal proof of A equal B. On the other hand, the saturated set has them all, because it wants to have all the normal form proofs, and therefore it keeps also the equation A equal B, because it wants to have also the proof A goes to B in addition to this proof. This is also a valley proof, of course, because this can be 0. Okay? Of course, the notion depends on the ordering, because if we take the same set, A equal B, B equals C, A equals C, and the same notion of valley proofs as minimal proofs, but A and B are not comparable, so this symbol means that neither A is greater than B, nor B is greater than A, nor A and B are equal. So they are not comparable. Now, saturated and complete coincide. Why? Because also the saturated presentation does not want to have A equal B anymore, since with A and B are comparable, the proof of A equal B by the equation A equal B is this, with no orientation between A and B, since they are uncomparable. And this proof is not minimal with respect to that definition. Okay, now, based on the notion of proof orderings, a notion of canonicity was developed. We say that a presentation is contracted if it contains all and only the premises of its minimal proofs. And then we say that the presentation is canonical, and we represent it with this sharp symbol up here. So S sharp is the canonical presentation for the theory of S, if it contains all and only the premises of normal form proofs. Now, contracted means contain all and only the premises of minimal proofs. Canonical says normal form proofs. So if you think about it, it means that canonical is saturated and contracted, because the saturated is the one where, because there are all the normal form proofs, minimal and normal form essentially coincide. And then one can prove that one can also characterize a canonical presentation as the smallest saturated presentation with respect to subset ordering, and the simplest presentation with respect to the ordering on presentations based on the ordering on proofs. Now, all this applies to equational theories in the standard way that people may know from term rewriting. A normal form proof of a theorem for all x's s equal t is a valid proof connecting the scolemized forms of s and t. S with the hat is s, where all the variables are replaced by Scolem constants, and the same for t. Now, in this context, saturated means convergent, the traditional notion of rewriting systems that are confluent and terminating. Confluent means uniqueness of the normal form. Contracted will mean interreduced, so all the equations in the presentation are reduced by rewriting one with respect to the other. And canonical will be convergent and interreduced. And a canonical system, if it is finite, gives a decision procedure, but we all know that this is a rare event because, unfortunately, finite canonical presentations are difficult to find. However, they do exist for some fortunate theory. But now, let's go to see how redundancy changes if we use proof orderings rather than formula ordering as before. We can say that a clause is redundant if adding it to the set does not improve any of the minimal proofs. So the set of minimal proofs that we have in the presentation S is the same as the set of minimal proofs that we have in the presentation with C added, because C is redundant, it doesn't help. Or dually, we can say C is redundant if removing it does not worsen proofs. So if we have S and we remove C from S, S minus C is simpler, is smaller, is simpler, because its proofs are better, because C is irrelevant for the minimal proofs, for the good proofs. Now, working with proof orderings, we are going to view inferences as a sort of proof reduction. Both expansion inferences and contraction inferences will be seen as proof reduction. And we say that an inference is good if it infers Si plus 1 from Si, and Si plus 1 is simpler than Si, so it has better proofs, better or equal proofs, nothing gets worse. And the whole derivation is good if this happens at all the steps, for all i's. Now, an important property of good derivations in theorem proving can be synthesized by saying once redundant, always redundant. So if something becomes redundant at some point, it will be redundant forever. So we can commit to throw it away, and it will never need to come back. This is why these inference systems, although they venture to remove data, they can do so permanently, and therefore they are also what is called proof confluent, in the sense that they don't need backtracking to go back and possibly put back something that was removed before. So formally, if we take the intersection of what is in Si plus 1 and was redundant in Si, it is also redundant in Si plus 1. So if it was redundant before and it is still there, it is redundant also in Si plus 1. So essentially, once we throw it away, that's forever. Now, I already talked about expansion and contraction, and here comes the formal definition. Expansion means adding logical consequences. So from A, we infer A union B, where B are logical consequences of A. Contraction means that we remove something. We remove B. From A union B, we go to having only A. But we want A to be simpler than A union B, which means they are equivalent. So whatever I throw away is still a logical consequence of what I keep. And moreover, what I keep has better or equal proofs. And both expansions and contractions are good. I mean, expansion is trivially good because if I only add things, the proofs are not going to worsen because I have everything I had before. The crucial thing is that contraction doesn't make the proofs worse. Now, I can then qualify derivations based on the properties they assure to the limit. So I'm going to say that a derivation is saturating if it generates a saturated limit. I'm going to say it is complete if it generates a complete limit, contracting if it generates a contracted limit, and finally canonical if it is a saturating and contracting. So it generates a saturated and contracted limit, which is canonical. Now, fairness at last. How can we define fairness based on proof orderings? So what is the intuition? we would like that when at a stage of a derivation, say Si, there exists a minimal proof of the target theorem, that is the specific theorem we would like to prove, not all the possible theorems in the theory, which is reducible by our inferences, by an expansion or contraction inference, then it will be reduced eventually. Now, how can we write this formally? We can say for all I greater or equal than 0 and for all proofs P of the target theorem that we are interested in that is minimal at stage Si, if there exist inferences from Si that take infinitely many steps to some S prime, and there is a proof Q in the minimal proofs in S prime, which is strictly smaller than P, then we would like to have a stage J in our derivation greater than I, such that there exists a proof R in the set of minimal proofs provided by this Sj, such that R is smaller or equal in the proof ordering than this Q that was better in P. This notion applies to both expansion and contraction. So while the the classical notion of fairness focuses only on expansion, this one treat expansion and contraction both as first-class citizens, because it emphasizes that contraction is not only deletion, but it is also generation of reduced forms of clauses like in simplification. Now, how can we instantiate this intuition? Because, I mean, this one is nice, but basically it says a desideratum more than how to achieve it. We would like that when a reduction is possible, somehow we will get it. So how can we point out exactly how to achieve this? We need a notion of critical proof, because in the realm of all the possible so if we don't want to do saturation, which means reducing everything essentially, we need to focus on something. And so we need a notion of critical proofs. So a critical proof is a minimal proof which is not in normal form, but such that all its proper subproofs are in normal form. And the classical example in equational theories is a peak, that is a proof done like that, where we have something and the possibility of going down from U to S or to T. This is what typically a superposition step does. A superposition step will detect these and will generate these and then possibly orient it into one way or the other. So then we call CS the set of critical proofs of S. And as usual, we are going to look at the critical proofs with persistent premises. So we look at those. And we say that a derivation is fair if eventually it manages to reduce all the critical proofs. So for all the critical proofs from persistent premises, there exists some proof in the sets that I'm going generating in the derivation that is strictly smaller. Now, how about uniform fairness? How we recover it in this proof ordering-based framework? Now, uniform fairness will be a stronger property. So we call trivial proof a proof made of the theorem itself. So we put a hat on S to denote the set of all the trivial proofs of formulae in S. Then the trivial proofs with persistent premises is S infinity with the hat. And then uniform fairness will say that all these trivial proofs that are in the persistent set, except those that needs to be in the canonical system, will be reduced eventually. So it's a stronger property than fairness. And we show it with these theorems. So we show that if the derivation is fair, then it is completing, which means the limit is complete. The derivation is uniformly fair if and only if it is saturating. So it gives saturation, and if there is a saturation in the end, it must be uniformly fair. That's an if and only if. And fairness is sufficient for theorem proving, for proof search rather than saturation. Essentially, it is not necessary to add all consequences of critical proofs, but just enough to provide a smaller proof for each critical proof. Now, this is all nice in theory, but in practice, it is still a challenge because we only have a set of clauses in practice. The proofs are not there. The proofs only exist implicitly. It's not that we have explicitly a proof and we know how to reduce it. So the question is, which properties the search plan should have to try to approximate in practice this desirable fairness property. Although I claim that already having, at least in theory, a notion of fairness that earns something weaker than saturation is a good thing, because at least it makes it possible to work towards fair search plans that are not uniformly fair. Anyway, we want a search plan to schedule enough expansion and contraction to be fair and therefore completing. It should schedule enough contraction to be contracting. And we also want it in practice to schedule contraction before expansion. So we talk about eager contraction. How does this happen in existing theorem provers? We need to distinguish between two forms of contraction, forward contraction and backward contraction. Forward contraction is when we have generated by expansion, for instance by resolution or superposition, a new clause C, and we contracted with respect to previously existing, already existing clauses, and we get a reduced form C prime. Backward contraction is when we use C prime to contract, to possibly reduce, simplify, subsume the already existing clauses. Now, a first basic idea in the implementation of theorem provers is to implement backward contraction by forward contraction. Usually one uses an indexing scheme to detect that the clause is reducible, and then once that has been detected, the reducible clause is just treated like if it were a new clause and subject to forward contraction. So we really need only one procedure for the two. And then, what does it mean to have eager contraction? Ideally, we would like that at every stage I, there is no redundancy in Si, but that's not possible if every step represents a single inference. So what we can get in practice is that periodically the set of redundant clauses at stage I is empty. For instance, the existing theorem provers implement the given clause loop, which means they execute a cycle whereby at every iteration they select a clause and they perform all possible steps between that clause and the clauses that were already selected before. Now, these two sets are usually called active and passive. Active are the clauses that were already selected as given clauses and that therefore are used as premises for expansion inferences. That's why they're called active. Whereas passive contains all the other clauses that have been already generated but have not been selected yet for inferences. Now, a given closed loop may do enough contraction to keep the union of active and passive interreduced. So that's the most aggressive contracting strategy. A more prudent one that decides to invest less in contraction, is to keep only the active set interreduced, because since we don't want to use redundant clauses for expansion inferences, it is enough to keep interreduced the set out of which we are going to get the premises for expansion. And most theorem provers implement both these two search plans, and sometimes one is better, sometimes the other is better. Now, let's see an example of the kind of aggressive contraction that we can get with this kind of framework. For instance, working with conditional equations now to go beyond the equational the equational theories and see also conditional equational theories or Horn equational theories. Assume that we have A equal B implies FA equals C, and A equal B implies FB equals C. Now, assume that we have an ordering where F, the ordering on symbols, is F is greater than A is greater than B is greater than C. Then, A equal B implies FA equals C reduces to A equal B implies C equals C. And because C equals C is trivial, this can be deleted. So how does this reduction happen? Because A equal B is the same condition, so we can, the idea is that we use the condition itself to do rewriting. So this A reduces to B, and then because FB is equal to C, FB reduces to C. And so the entire first clause can go away. So the idea is that we can use also the conditions as the right roles. For another example, say we have A greater than B, A greater than C. This set, A equal B implies B equals C, A equal B implies A equals C, is saturated. The set with only A equal B implies B equals C is equivalent. It is the same theory. It is complete but not saturated. You see that it is smaller. It doesn't have A equal B implies A equals C. And it is reduced. Why? Why can we get rid of A equal B implies A equals C? Because this conditional equation can self-reduce, can reduce itself to A equal B implies B equals C, which is subsumed by the other copy of A equal B implies B equals C, which we already have. Because again, we allow also the condition to be used for rewriting so that this A goes to B. Alternatively, we can reduce A equal B implies A equals C to A equals C implies A equals C. Why? Because under A equal B, we can, we can reduce the B to the C this time. And so where is it? No. Oh, yes, we are reducing the B in the condition to C by using this one. A equal B implies B equals C, so this B goes to C, and this is also to be deleted because it's trivial. Anyway, to summarize, the idea is that fairness should yield something weaker than saturation. This can be achieved in the theoretical framework of definitions by adopting proof orderings as opposed to formula orderings. And this opens the possibility to study non-trivially fair and eager contracting search plans and to prove them fair. And this is, in my opinion, valuable to reduce the gap between the theory about theorem-proving, which always asks us to get saturation, and even theorem-proving is presented as saturation-based strategies, and the search plans and the techniques that we have in practice which usually allow more contraction. And the claim is that that can be done not at the expense of completeness by preserving this weaker notion of fairness. And this is all I have. Thank you very much. Some references. These are some papers where this kind of work was developed. So if there are any questions, I'd be happy to take them. Well, I mean, I realize that it is somewhat abstract and theoretical topics. It's been with me a long time, actually, because you see 2013, 2007, 1995, this actually was a paper publishing results in my PhD thesis, because I had this notion that we should do less than saturation ever since then, and it is something that I worked on over time more than once, because I really think that the very same notion of saturation-based theorem-proving, the name itself is somewhat misleading. I mean, why should we want to do saturation when in reality we are searching for one specific, for at least one proof of one specific theorem? So saturation is too much, and we should focus more on weaker requirements that may also bring the theory and the practice of theorem-proving closer by giving more importance to contraction and fair but not uniformly fair search plans. Please.
I was wondering if, I was wondering how the different, can you compare the type of fairness that you discussed here with some of the standard definition of fairness for scheduling in a concurrent basically setting? And so there's things like weak fairness, strong weak fairness, etc. If you see, for instance, if every kind of, I'm not an expert, it's family of techniques, like let's say expansion versus contraction, for instance, and if you see at different like concurrent processes each, for instance, but I don't know if this is related. I mean, if there's a way to have a mapping, or it's just completely different, basically. And the guarantees that you get, I guess, also are kind of different here, but I'm not sure. I mean,
that's a very good point, thank you. I don't think that the theorem-proving community took inspiration from the notions of fairness in other fields of computing. And that's probably something that we should look into. But because fairness was enshrined pretty early as something that should produce this saturation effect, somehow that was sealed that way, and the very same theorem-proving methods based on superposition and resolution was called saturation-based, and that was it. And so fairness was no longer a problem. And somehow I've been contending for all these years that fairness is something to be discussed instead, that we should weaken that notion, and maybe precisely looking at how fairness is defined in other fields, we might get inspiration for non-trivial, practical, fair search plans. So that's thank you, that's a nice lead.
Or maybe also, I mean, in some sense, I mean, I'm not an expert of fairness either for concurrent system, but there are only, I mean, there are maybe a few standard notions of fairness. I don't know how many they are. But then there is a more general kind of notion of fairness for algorithmic, I mean, for algorithms, basically.
Right.
And so, and that's the concurrency setting doesn't perhaps address. This is perhaps closer to that, or more general in a way.
Right.
But I don't know if there's like this kind of meta theory of fairness, so to speak, or whatever. I don't know.
But if I may, I mean, consider also how we don't really discuss much fairness for decision procedures. I mean, this whole theoretical framework about saturation was done for first-order theorem-proving, where all we have is a semi-decision procedure, and things, you know, in general, it's infinite, so we have this search process, and we view it as a saturation, this accumulation process. But also in decision procedures, there is a search, because even if the search space is finite, we still don't want to be exhaustive, because it's huge. So the question of studying more fairness also for decision procedure, the order with which we do things, in my opinion, should be relevant. And somehow, this is a topic that has not gotten much attention because much of the effort went into designing the refutationally complete inference system, and then the decision procedure that are complete in the sense of being able to generate the proof on the one hand or the model on the other. But I think that also there we could discuss what does it mean to be fair in practice and how we can best do it.
So I have a question about that.
Yes.
Let's consider propositional logic and the satisfiability question for it. So what I don't understand is that how can fairness or paying attention to fairness, it cannot help us in the worst case, right? In the worst case, you have to be exhaustive.
Right.
So what is the point of it? Is it that it gives you some heuristics that if the thing is that in some cases, maybe hopefully related to practical problems that arise, you terminate faster?
I would say two things. On the one hand, it can inspire heuristics. On the other hand, we cannot improve. Okay, for a decision procedure, the search space is finite. We have an algorithm, and therefore we also have the classical notion of complexity. We know that it is exponential, so we cannot do better than that in the worst case. However, we can investigate other notion of complexity, because one can investigate notions of proof complexity, one can investigate notion of search complexity. So although the search space remains exponential, I can still compare two procedures by which part of the search space they visit, for instance. So we could develop measures, say orderings, that capture how large is the search space visited by one and how large is the search space visited by the other, and establish a comparative result which doesn't change the fact that in the worst case it's exponential, but it can say that, for instance, for a certain class of input, strategy A generates a smaller search space than strategy B. So this is also something that might be useful to investigate if we see fairness as something to be discussed also for decision procedures. Any more questions? Thank you very much for coming and for listening.